going to be talking about evaluations, and it's actually really kind of a nice tie-in to the end of Tom's talk previously, as he was talking about the need for evaluation-specific metrics, or I'm sorry, application-specific metrics, which is absolutely the case in my experience as well, that these machine learning algorithms, your understanding of these machine learning algorithms is only as good as the metrics you're using to evaluate their performance. And the closer you can get metric-wise to your actual loss function, to what you actually want to get out of this, out of the model that you've created, the closer you can get to defining that precisely, it actually helps you inform your decisions about modeling. It helps you inform your decisions about the infrastructure you need around the model. So making that precise has benefits for you, the practitioner, as well, because it allows you to really define the problem you're trying to solve. And so to help you out with that, we're just going to kind of, again, step back. For those of you who don't know a lot of the terminology around evaluating machine learning models, we're kind of going to give a primer of that terminology, and then also just give you some hints about what metrics you might find interesting in practice, or if you have a metric that we don't usually report in the machine learning world, how to construct your own metric for evaluating whether or not your machine learning model is doing what you think it should. Okay, so step one here is that you've created a model on some data. I trained a model on this data, and oh yeah, it seems really good. I look at it in the interface, I look at the tree breakdown, I look at the partial dependency plot. It seems like it's doing the things that it should be doing. But how do you know for sure? And the way we know for sure in machine learning is to quantify the model's performance in some way. And to quantify the model's performance, we have to evaluate it. This isn't an optional step. This isn't stuff you can just ignore if you're going to put a machine learning model in production. You can't just train a model and then put it out there and expect, anything out of it. There's no way to have any idea what it's going to do unless you actually make it work for you for a while. It would be the equivalent of building a car and then not driving it. You don't know how it's going to drive until you actually sit down behind the wheel and drive it. So proper evaluation. So there's kind of three bits that I like to think of about evaluating a model in the correct way. The first one is choosing the right metric. As Tom was talking about, if you don't choose the right thing to measure, you're not going to know how your model performs in a way that's meaningful to you. Second, you have to test on the correct data, which might be harder than you'd think. Holding out the correct data for testing can get a little tricky, and it can get a little tricky in a way that's really annoying and dangerous. And I'll get more into what that is in a minute. And then third rather, you have to replicate your tests. So as Tom was talking about earlier, there's a lot of uncertainty in the world. There's data uncertainty, there's model uncertainty, and you want to get a sense of that variance by doing multiple tests. So first of all, choosing the right metric. So stepping back again, the most basic workflow for model evaluation is you have a data set, and you typically split it into two separate data sets for training, one for training and one for testing. You train a model on the training subset of your data, and then you measure the performance of that model on the test data. And what you're trying to do here, when you do this, when you split the training data, is you're trying to simulate for the model what it's going to see in the future, which is data that it's never seen before, right? The data that comes in the future is going to be data that the model did not see in training. So you're trying to simulate that. And if the training data is representative of what you're going to see in the future, that is, if you hold out some of this data, does it look like the data you're going to see in the future? If it does, then the performance that you're given by this process is going to be representative of the performance you'll see on future data. So you're trying to simulate the future with this by holding out some test data. And what do we mean by performance here? Well, this is where you, the domain expert, the practitioner, come in. You have to define, again, as Tom said, an application-specific metric for your performance. It might be very close or exactly one of the ones that we usually report in machine learning, but even when it is, you still have a choice to make. Like in the medical community, as Tom said, they use AUC and they use it regularly, and it works for them because it's very close to the actual thing that they're trying to optimize. And that's good for them, but it might not be the right thing for you who has an entirely different problem. And so how do we go about picking a good metric? Well, let's go back to medical testing example, where, as we say, they use the AUC typically, but for purposes of argument, let's just say that we need to pick something useful here for this particular problem. So we have an ML model that'll diagnose a disease, and let's say about 1 in 1,000 people who are tested by the model turn out to have the disease. So we have really unbalanced data, right? We have a data where 1 person out of every 1,000 is positive and the rest are negative. Let's call the people who have the disease sick, just for purposes of vocabulary here, and let's call the people who don't have the disease well. So how well are we going to do when we make these predictions on a test set? First, let's define a little bit of terminology. In this terminology, the sick people are positive and the well people are negative for the test. And we're going to define 4 classes of result that can arise from your prediction. It's a true positive if you're sick, but the model also realized you were sick. It's a false positive if you're well, but the model said you were sick. It's a true negative if you're well and the model said you were well, and it's a false negative if you're sick, but the model said you were well. In this case, notice that positive and negative means sick and not sick, and true and false means the model got it right or the model didn't. So you have a little square, a 2x2 square of possible outcomes, whether the model got the prediction right and whether the true class is either positive or negative, sick or well. Okay, so the easiest way to evaluate the model is accuracy, right? You just take the number of things you got right and you divide it by the total number of things in your data. It's percent correct, like an exam. So how many patients did I pick the right answer for? If the accuracy is 1, then that means you didn't make any mistakes. If the accuracy is 0, then that means you made a mistake on every single prediction that you made. It's intuitive, right? It's just like an exam score, but it's not always useful. Partially because you can't really compare the accuracy on one problem to the accuracy on another problem where the balance in the data is different. So for example, remember in this problem, we have only 1 in 1,000 people who have this disease. So if you always predict a person is well, let's just say somebody walks in the door, you don't take any measurements at all, you just predict you're well, that's your model, you're gonna be 99.9% accurate. And so that for other problems, like if you're actually taking a test in school, that seems really good, right? That's an A. But in this problem, it's absolutely an F. It's nothing that's even remotely useful. So we have this problem where accuracy on unbalanced data gives us a number that could be crazy high, but that's spurious. The value of the number is sometimes not useful. And I mean, you can also go the other way, right? You can imagine a model that's 99.8% useful or 99.8% accurate, but also picks up every single person who's sick. And that model is extremely useful, even though the accuracy is lower. So accuracy, not a great metric. So what if we want to do some more elaborate things? Tom mentioned precision in the last talk. So what is precision? By precision, we mean in this case, how well did we do when we predicted someone was sick? So let's say we have this data set of 11 people here, and we see on the left that we predicted 5 of those people were sick, and we predicted, oh, I'm sorry, it's more than 11 people, isn't it? No, it's 11. We predicted 5 of those people are sick, and we predicted 6 of those people are well. So we're only, when we look at precision of a model, we're only looking at the times that we predicted someone is sick. And you can see in this case, when we predicted someone was sick, we were right 60% of the time. 3 of those people actually were sick, and 2 of them were well. So the upshot of this is that a test with high precision has very few false positives. A precision of 1.0 indicates that every time we say somebody is sick, they're actually sick. So we're right 100% of the time when we say somebody is sick. However, it doesn't say anything about people that we predict are well, right? There could be a whole bunch of sick people that we're predicting are well. Precision would not tell us. They only tell us the results when we predict somebody is sick. Recall is sort of the opposite of this thing. Recall is how well do we predict when somebody actually is sick. So we have 4 people who are sick in this data set, the 4 red dots, and you can see that we predict sick for 3 of them, right? So we have 3 true positives plus divided by 4 total people who are sick, true positives plus false negatives, and that gives us a recall of 0.75. In other words, we found 3/4 of the people who are sick. If you have a test with high recall, it indicates very few false negatives. It doesn't say anything about the people who are not sick. It only says, it only gives the result for the people who are sick. Recall of 1.0 means you picked up everybody. You found everybody who was sick. Recall of 1.0 is good, right? Unfortunately, it doesn't say anything about false positives. So if you have a recall of 1.0, that's good. You've picked up all the people who are sick, but you also might have picked up millions of people who are not sick. And so again, you imagine a test where, well, I think I'm getting to this here. Yeah, you can trivially maximize both measures. So with precision, if you just pick a single person and label them as sick, you can probably find one person who's sick. They have all of the indicators. They're an easy case to label. You can probably find one person who's sick and then label everybody else not sick. Now that means you have a precision of 1.0, right? The only time you labeled someone sick, you were right. That's really high precision. Unfortunately, the recall is terrible because you only found one person who was sick also. On the other hand, if you label everybody sick, you have a trivial model. You walk in the door of the doctor's office, they just say, yes, you're sick before even doing any tests, then of course you're going to pick up everyone who's sick, right? Everyone who's sick who walks in the door gets labeled sick, but also everyone who's not sick, everyone who's well is also getting labeled sick when they walk in the door. And so you're guaranteed perfect recall, but it's still, again, a useless model for the purposes of determining who's sick and who's not. What you want is a model that has high precision and also high recall, right? You want both, but unfortunately, maximizing one, making one go up, making recall go up means you pull in more people, which is generally going to lower your precision. And if you want to make your precision go up, that means you have to be more picky about who you're going to label sick, and that means your recall is going to go down. So you have to strike this balance, right? There's very much a trade-off here to be made between precision and recall. And there's some scores that are reported in the literature, the F1 score, the phi or Matthews correlation coefficient, that attempt to deal with this issue, to try to give you a single number you can look at, and when that number is high, oh, I have high precision and high recall, I know that. But now you run into another problem, right? There's a problem where a false negative and a false positive don't necessarily have the same cost. For example, in the medical problem, if somebody comes in and they're sick and you say, oh no, you're fine, go home, you know, you're not having any problems, then there's a bunch of things, a bunch of bad things that could possibly happen, right? They could get sicker, they could need hospitalization, they could die, they could give their sickness to other people. Sending somebody home who's actually sick is a really poor outcome. On the other hand, if you label somebody sick and they're actually well, the outcome isn't nearly as bad. You say, oh, you're sick, you should stay in the hospital for a few days or something. So they stay in the hospital for a few days. They're not sick, so nothing really happens. They continue to do tests. Eventually they get let out. But really the only thing that you lose here is the money that was spent keeping this person in the hospital or having them stay at home or giving them unnecessary medication. There's not much you've lost by accidentally making this mistake. So you've got a case where one mistake is worth way more than another, and you can make your own metric here in this kind of simple case by just multiplying the number of times you make the mistake by the cost of that mistake, and then you get a cost for operating the model, and that cost can help you choose between models. It can tell you if you're improving. It can tell you if your modeling techniques are giving you something better. But the point is, you've defined kind of an exact cost. And this 1 in 100 here, it could be dollars, or it could be utils, or it could be anything you want. All you have to do is say yes, this is 100 times worse than this, or this is 50 times worse than this. And once you make that determination, you have a model, you have a way of evaluating models where you can say, you know, according to my own logic about the situation, this thing is better, or according to my own, the cost that I've assigned, this thing is worse. So this, if you can break down the costs in kind of this simple way, it can give you a really precise idea of whether one model is performing better or worse than another. And these costs, like there's a lot that goes into account, right? There's social issues and there's human issues that go into account that you're trying to quantify, which can be difficult. But remember, you're not making like kind of a moral determination of what's, you know, something better or something worse. You're telling the algorithm, hey, this is valued more than this, right? And so all you're doing really is you're giving yourself a chance to choose the more meaningful model instead of just pulling something off the shelf, pulling a metric off the shelf that may or may not equate to any human value. Yeah, so for example, a way that this cost could change, what if the positive diagnosis results in expensive or painful treatment? Well, that might make you think twice, right? Then maybe it isn't completely penalty-free to tell somebody who's sick if they're not. Maybe there is some human cost to that you want to take into account here. So yeah, it can be difficult to assign numbers to these costs, but the alternative is to not assign any numbers to the cost and then just get whatever has worked for people in entirely different domains in the past. Another thing I just want to mention here is operating thresholds. So most classifiers don't just give you a prediction, they give you a probability score. And then the prediction you assign to an instance is a function of the score. That is, if the score, you know, the model says with a score greater than 0.5, that this thing is true, then we're going to predict true. If it says with a score that's, you know, less than 0.5, then we're going to predict false. When you can experiment with thresholds along an ROC curve to see how your metric changes when you change the threshold. So if you lower the probability threshold, you can imagine, okay, I'm going to predict true whenever the model score is above 0.2 instead of 0.5. So if you lower the threshold, that means you're going to be more eager to predict the positive class. What's going to happen? You're going to increase the recall, right? You're going to predict positive more often, so you're going to pick up more of those points that are positive, but also you're going to introduce false positives in there. And then if you increase the threshold, you say, okay, I want to score all the way up to 0.8 before I'm going to predict true. Then you're going to predict the positive class less often. You're going to be pickier about when you predict the positive class, which will probably increase precision because then you're only taking the highest scored points as being the positive one, but it's going to lower your recall. So again, this slider represents a trade-off between precision and recall. And I do have a quick example of this right here, which is a ROC curve I've constructed at BigML. So you can see this is a diabetes data set, the classic diabetes data set. And here the positive class is true. And you can see I have an ROC curve over here that represents my true positive rate on one axis and my false positive rate on the other axis. So this is basically, okay, if I want to pick up this number of true positives, 80%, I have to put up with 30% false positives. So that's what this curve says. And here we have the confusion matrix, which tells you, okay, here's the cases where this is true and I predicted true. So these are my true positives. Here's cases where the actual class was false, but I predicted true. So here's the false positives. And then here's my precision down here, the true positives over all of the cases where I predicted positive. And similarly, you can see the recall over here. And so here's the precision recall trade-off. And then here's my probability threshold up here. So if I move that probability threshold around, I can change the precision and the recall of the classifier. So like we're at a 50% probability threshold now. Let's bring it all the way down to 0.2, let's say. And you can see what's happened here. I have lower precision because again, I'm not being as picky with the points that I'm going to classify as positive, but also my recall is much higher, right? My recall has went up all the way to 90%. this is a diabetes data set, so I'm labeling 9 out of 10 people who have diabetes correctly. So I'm picking up almost everyone. I've sacrificed a little bit of precision to get very high recall. Similarly, if I move this probability threshold up, I say, okay, let's make it really picky. Let's say we got to get all the way up to 0.8 before I predict that a person has diabetes. Well, now I'm very picky about when I say somebody has diabetes, so I'm only picking up 1 in 4 people who have diabetes. So recall has really gone into the tank. My recall is really terrible now. But on the other hand, my precision has went up to 70%. So when I do predict someone has diabetes, I'm a lot more sure of myself than I was when I was less picky about his prediction. So if you want, if you're interested in this trade-off, you can slide this probability threshold around, and you can see what happens to this confusion matrix, what happens to these precision recall values as you move this around. And that gives you a sense of, okay, maybe the default threshold of 50% is not acceptable, but maybe if I slide this around, I can find a distribution of predictions here that I think is acceptable, that will work in my domain. I'm willing to sacrifice this many, I'm willing to sacrifice this much recall for this much precision, or vice versa. And again, if you have those costs defined in the cost matrix slide I showed you before, you can apply those costs here just as well as anything else, and you can kind of optimize this threshold to be as low cost as you can find in here. So now just briefly talking about holding out data. Why do we split this training data, the training data into training and test sets? Again, like I said before, we're trying to simulate the future for the algorithm, and we always do this. This is something that's definitely not optional. We always have to test on data we don't see in training. And another reason, another way to say this is because machine learning algorithms are really good at memorizing data. We don't care how the algorithm performs on data that it's already seen because it already knows that data. It's already memorized it. This is like a database, right? If you put a point in the database and you ask to predict the objective on that point, it's already sitting there in the database. You just have to look it up. So for example, here, like we have these specific values for a diabetes model. And if we evaluate on those exact same values, then we can just look up in the model, oh, when we see those values, the prediction should be this. And so you can trivially get it right just by remembering the values you saw in training. And to kind of see this even more clearly, imagine that instead of plasma glucose and BPI and things, BMI and things that are relative to diabetes, imagine that the feature was just a person's name. This would still work, right? If you had a person named Bob in the data set, and then you say, give me a prediction for Bob, the model would say, oh yeah, Bob, he's in the training data, he has diabetes. This is completely meaningless, right? If your name is Bob, you're no more or less likely to have diabetes. And yet, because the model has memorized all the data, it would be able to predict exactly correctly. So you always want to split your training and evaluation, split your training and test data so that your model can't just rely on memorization to make the correct predictions. Okay, so that's pretty clear, right? You just hold out a random part of your data set and then you're good, right? You're not testing on the training data, you're done. No, that's totally wrong. There's other things to worry about here when you hold out data. Mainly, the thing you're trying to avoid is information leakage between the training and the test data. So what's information leakage? Well, as an example here, let's try to predict the stock market, the closing price of the stock market. Let's hold out 10 random days in the stock market and see if I can predict the correct price, the correct closing price for those 10 random days. That's going to be pretty easy, right? If you just hold out a random day from the data set, you know the opening price of the previous day, and you know the opening price of the next day. So probably the closing price of that day is going to be in between the opening prices of the day before and the day after. And because you've just selected a random day as holdout data, you get to know the day before and the day after. The day before and the day after are probably in your training set. So even though you don't have that exact day in the test set, you have information about that day that comes from the day before and the day after. So this makes the problem much easier than it is in reality, right? When you go to use this model in reality, you're not going to know what happens the next day. You're not going to know what the price of what the opening price is on the following day. You're going to have to guess without that information. So you're going to end up with a model that isn't going to it's going to, when you do this test with the model, it's going to have very high performance. Then when you go to use it in the real world, you're going to find that it does not perform nearly as well. Now let's say, what if we hold out the last 10 days and try to predict on those? Now that's very different, right? Now we don't have any information about the future in our data set because we just held out the very end. We didn't hold out any data from after that. And so now you're doing a more realistic test, right? You're training on the past, testing on the future. That's exactly what's going to happen in the real world when you go to deploy the model. So you can't just hold out random rows in this data set. You actually have to hold out the end of the data set in the temporal sense. This is really common when you have time distributed data like this, where you have to watch out for, you can't hold out random instances because they all have information about one another. But it can also happen in other places. Like, for example, this is an example from my real life. Let's say we have a data set of 10,000 pictures from 20 people, and each was labeled with the year in which it was taken. So we're trying to predict the year from the image using things like the dye fade, borders on the photo, the watermark on the paper that was used, any sort of printing with the date. We're just trying to estimate the year it was taken from any information we can get from the image. So the problem here is that if we hold out random data, we're going to have data in both our training and test sets from every user, probably, right? So for example, if you hold out, if you have a user who contributed 1,000 photos to this set, you're going to have 900 of them in your training data, and you're going to have another 100 in your test data. But those photos are going to have information about each other, right? Very few people will just randomly take a picture at random times. There's going to be some similarity between the photos from one user in the training data and the photos from that same user in the test data. They're going to have been taken by the same camera. They're probably going to have been taken around the same time. They're going to be stored in the same way. So if you know the year for 900 of those photos, you can probably guess the year for the other 100 just by using the information that you already have. Why is this a problem? Because when a new user comes to you with new photos, with cameras that you've never seen before, stored in conditions that you've never seen before, taken in years that maybe don't appear as often in your test data or in your training data, then you've got a problem, right? You've never seen any of these users before, so you don't have any of that extra information. And so the solution here is to hold out whole users instead of just random values. You've got 20 users, use 18 of those for training and hold out 2 of those users for testing and see how you do on those 2 users. And in the system we actually developed, it was a decrease, we decreased our accuracy, our performance accuracy by something like 10 or 15% when we held out users instead of random instances. So this was a big deal. Like, it was a huge step down in performance and indicated that we had to do something that generalized a little better to more users, or we needed more users for training. So how do we avoid this? It's a terrible problem, because if you make the mistake, then you'll get results that are really good, and you'll love that, right? You're trying to get good results. You want good results, and this will give you results that are too optimistic. And so it's the worst sort of problem to have, because you want to believe so badly that you've done all of this right. So you have to be careful. Do you have data where points can be grouped in time? Do you have data where points can be grouped by user? Do you have data where points can be grouped by location? Does all of your data fall into one of a small number of groups? Let's say you have 5 restaurants and you're trying to predict something about restaurants in general from these 5. Well, really, all of your points were generated by these 5 restaurants. And so the right thing to do to know what kind of performance you're going to have when a different restaurant, when you use this model on a new restaurant, you have to hold out all of the points generated by one of those restaurants and use the other 4 for training or something like that. you're trying to minimize the amount of information that one point has about another point in the same group. And even if you're suspicious that points from the same group might leak information to one another, just do the test. So if you say, yeah, I think all of the points from this restaurant-based problem, I think they're all being drawn from the same distribution, but it's possible that because I only have 5 restaurants, that some of the points from each restaurant are similar to one another, similar enough to leak information. So try a test. Just see what happens when you hold out one location, when you hold out, some subset of users, when you hold out, just the future instead of the past, and make sure you get the same results. If you do get the same results with that test as you do when you hold out random data, then you don't have any problems, right? You're doing the right thing on that particular axis. If you don't, if the results are dramatically different, then you have one of these leakage problems, and you've got to think more about that, either changing the features so that they're normalized across groups, or doing these elaborate holdout procedures where you hold out users or chunks of time instead of just individual random instances. And then finally, one test is not enough. So if you just do a single train and test split, you're relying on kind of the whims of randomness to give you the right answer. You've got randomness in there from the data, because the data set is only a finite number of points, and they're drawn from some distribution that's you could have more training data, and you don't. You happen to have the training set that you have. And so that's a source of randomness, that you happen to have these exact training points. If we're talking again about the medical domain, you happen to have the points where people came to this specific doctor at this specific place, or were chosen, released their information to you. There's some randomness amount around that data, right? You don't have every single person who could possibly have this disease. You have this small set of people. And so that's a random set that you have. And then the split that you make for training and testing is also done at random. So there's randomness kind of all over the place. And also algorithms themselves are randomized. The order of the data sometimes matters when you're learning. The best performing algorithms like random forests, isolation forests, clustering, deep nets, all of these have randomness built in. There's a random process that generates some step of the algorithm is driven by some random process in the middle. In general, this improves results, but it also increases variance. By changing the random seed of this process, you might get a different model from run to run. So an example of this is, okay, let's say I do a training and test split and I get this result, which I think is really good. But really, what we're talking about here is a distribution of results. One result is the result of a single random draw from this process where there's a ton of randomness in it. And so really, you're using this one result as an approximation to this whole distribution of results, which is faulty and kind of a scary thing to do. What you really want is you want to know about this distribution, right? You want to do a bunch of results so you get a sense of, okay, usually I get results are here. The tail of the distributions are, kind of on these extremes. And so that's the performance that I can expect to get when I roll this model out. If you just do one test, you don't have an idea about that distribution. And then when you're comparing models, it gets even worse. So here, for example, I've got a model. I've done a training and test split, and in one model, I set this mystery parameter value to 0, and the other one, I set this mystery parameter value to 1. This is real data, and this is an actual test that I did on BigML. These are random forests that I'm using here, and you can see that, oh, when I set the parameter to 1, performance is much better, right? Performance is around 0.5. When I set the parameter to 0, it's around 0.35. So clearly 1 is the superior value here, right? But if I do this same test 40 times, you can see that I just get an enormous amount of variance in performance. And this is, again, this is real data. The test set size here is about 150 points. The data set isn't particularly unbalanced. And yet there's just this massive variance in performance. And all I'm doing here, again, is changing the random seeds for the various random processes, the data set split, the random samples for the trees and the various other parameters for the random forest. All I'm changing is the seeds from run to run, and even so, I get this huge amount of variance in my results. And now, if you're like me, you look at those two sets of points and you think, oh, but it looks like we've gotten to the truth, right? Now it looks like the red points are a little bit higher than the blue points, right? So maybe 0 is the right value for this mystery parameter. And if you thought that, you would be wrong in the sense that the mystery parameter in this case is just the first digit of the random seed that I'm using. And so again, I've got a completely meaningless parameter. It's kind of meaningless by definition. I know that changing the random seed from 1 to 0, the first digit of the random seed from 1 to 0, is not going to produce meaningful improvement. And yet you and I, humans, are hardwired to kind of look for improvement wherever we can find it. Even when we do tests like this and see an amount of variance like this, we really want to believe that we found something, but we don't have actual proof according to these results. And in fact, if you run like statistical tests on these results, the rank tests or the paired t-test, you'll find that these results aren't statistically different. And so yeah, this is a meaningless exercise, and yet there are all these opportunities to find meaning in it. Here, I could have said that 1 was better. Here, I could have said that 0 was better. In reality, these parameters aren't meaningful, and so you have to watch out for that, especially when you're comparing models. If you don't do enough tests, you're not going to get to the truth, and the truth is often that there just isn't any difference between the performance of these two things that you can measure meaningfully. So always do more than 1 test. Never just do a single training and test split and then call it good. You've always got to do it more than once. And for every test you do, you should be varying the various random seeds of the processes used to generate these models. So try to experience as much of that variance as you can, because then that'll give you an idea of where your actual performance is. So cross-validation is a great way to do multiple tests. If you do the Monte Carlo version, where you don't exactly, where you don't split into folds, instead you just take random subsets, that can be useful. You can stratify. That's another really good technique to reduce the variance in your results a little bit. But yeah, definitely do more than 1 test, know what all these things are, and use them to the extent that you can. And don't just average and say, oh, this has a better average result over those 20 trials. That's the one that's better. That's not the interesting part of this. The interesting part of this is the variance you get from result to result, and whether or not that validates or invalidates any comparison you're making to any other reference point. Okay, summing up. First of all, choose the metric that makes the most sense for your problem. Just like Tom said, almost every problem out there requires you to make this choice. You have to choose a way of measuring the quality of the model that is in harmony with the problem that you have. Use held out data for testing and watch out for information leakage. So even if you hold out random values, you still might not be careful enough to separate your training and test data. Make sure that your points don't have information about one another, as they might if they're distributed in time, or if they're all generated by the same small set of processes. And then always do more than 1 test, varying all of the sources of randomness that you have control over, the random seeds of the algorithms, the random seeds of the dataset splits, and so on. I just recently wrote a blog about this, about machine learning benchmarking. If you want to read about it in a little more depth, you can go to the link at the bottom of the slide. And that's all I have.